Hello all. In this video we're going to continue our discussion of image thresholding, but this time we'll focus on thresholding algorithms, thresholding functions that work on color images. And sometimes they'll give us actual thresholds or they'll give us threshold-like images, but they are able to take advantage of the extra information that we have in color. So there's all of the previous examples we looked at were doing thresholding. They were working on grayscale images, as I said. There's a problem with that, which is that you lose a lot of information when you have something in grayscale. It is possible to have a shade of red and a shade of blue that both turn into the same grayscale value. That's an issue. It sticks us with a situation where we can't we lose the ability to distinguish those two from each other. Even though they're really different colors when they're in color, they could look the same when they're in grayscale. So it's nice to have an option that we can apply directly to a color image. And there is a function in OpenCV called inRange that does exactly that. So inRange expects a color image or an image that has a 3-channel representation. And then for each channel, I think I mentioned this before, for each channel you can give it a different range of values that are permissible. And it will only accept pixels when all 3 channels have values in the specified range. So we can use this on BGR images, but there are issues with that. So we have those pictures, the various pictures of, I'm going to switch back to just me, various pictures of me holding a ball of bright color in the camera view. So what I want you to do is take a good look at this ball, and in particular look at the color of the top edge of the ball versus the bottom edge of the ball. They're quite different. The colors on the top are very bright. They're very light, closing in towards white, and the ones at the bottom are very, very dark. This poses a problem for us with the BGR representation because in order to go from a light blue to a dark blue, not just the blue channel changes. All 3 channels have to change in order to stay the same hue while we change brightness, because every hue is a combination of the red, green, and blue values. So it's difficult with BGR to do a good job with this inRange function. Let's go back to my notes again. So what we typically do instead is we convert the image to an HSV representation and we focus on the hue channel, and that works much better for lighting conditions where things might be significantly different in brightness from one part of the object to another. I do want to remind you, I believe we discussed this earlier, but I wanted to remind you again here because we're going to be picking specific values and it's easy to make a mistake. When you're looking at HSV on, say, a color picker that you find on the web, it will give you often numbers between 0 and 359 for the hue, because that's how the hue is defined in most HSV. It's defined to be a number that is a degree around a circle from 0 to 360, but we leave out the 360 just like we always do, so it'll stop at 359. And you'll often see saturation and numbers that are either between 0 and 1 or between 0 and 100, because they're kind of thinking of those as a percentage. What percentage from the bottom to the top have we gone? Are we 50% up? Are we 75% up? And so forth. We don't really want to do that with OpenCV. We want to maximize our representation while staying within the uint8 framework. So we want to stick to numbers between 0 and 255, but we also want those to give us as rich a representation of the hue, saturation, and value as we can get. So the 2 bullet points here are what's critical. OpenCV uses numbers from 0 to 179 to represent hues. it takes that 0 to 360 and it divides it in half. So if we had a hue that was 250, let's make it an even number, 260 out there in a color picker, in OpenCV it would be half of that, or 130. That's how we would represent the exact same hue. We also map saturation and value numbers to the full range from 0 to 255. So if a color picker out there says the saturation should be 100, you want to set that saturation to 255. And if it says it should be 50, you set it to 128, and so forth. So you have to make this little translation when you're talking about HSV values in OpenCV, because they made choices in the representation to maximize the expressiveness at the expense of matching other sources. All right, I have a code example here. I'm actually going to go over to the code and we'll take a look at it and then we'll run it. So here I'm reading in a particular picture. It's a picture of me holding a bright green ball in my robot lab from some years ago. I am going to take a look at what happens first. I convert it to grayscale and I'm going to call the threshold function. Where is it? Here. I'm going to have it do OTSU, the OTSU adaptive thresholding, and run it on the gray ball, doing binary thresholding as well. So what we would love to have happen is that the ball pops out and the background and eye all disappear. The other thing I'm going to do is to convert the ball image to HSV. That's what's happening right here. I'm not going to imshow the HSV image. We know that would look weird because imshow does not understand HSV. It expects it to be a BGR. But what I am going to do is to call inRange. The inRange function takes in our HSV version of the picture, and then this first part here are the low values for the threshold, and the second part here are the high values. Notice the third channel is bounded from 0 to 255, and what that means is I'm saying in terms of value, brightness, any value in the range is fine. 0 to 255, they're all great. So we're basically allowing any value. And for the saturation, I've set it so that it goes from 10 to 255. I'm only eliminating things that are below 10 in saturation. And the reason I did that is when you get down to that level in terms of saturation, if you remember, that's like how intense the color is. When you get down to that level, things look gray. Between 0 and 10, they pretty much just look gray. So I want to eliminate things that look gray from consideration. So I set the bottom end of that range to be 10. What's narrow is the hues. I start the hue value at 45 and I go up to 65. I did this by, I actually took this image and I just selected pixels and looked at their HSV values and looked at some brighter pixels and some darker pixels and found that the range varied pretty much from, say, right around 50 to 60, and then I added a little bit of padding to that on the end. All right, let's go to the desktop and we're going to run this and see what it looks like. It popped up before, so here it is again. I think I have the original here as well, so I'm going to have to set these out and line them all up. Okay, so here I have the original color image and I have the grayscale that I generated. Here is the best that the binary thresholding with the OTSU algorithm for adaptive thresholding could do. It had no idea what I was looking for. So it ended up picking most of my face, most of the background. It did pick the ball because it is one of the brighter objects in the space, even in grayscale. Didn't really help us. But look at what I got out of inRange. that's pretty good. There's some noise right around the top edge of the ball. I could probably, if I really wanted to, I could try to tweak this, but I may not need to. If I just need to know generally where the ball is, this is perfectly good. It looks a little dented right here and on the other side. It's not a nice round surface. That's my fingers. My fingers are intruding into the space of the ball because I'm holding it, and therefore, they're blocking that part of the ball. So inRange is clearly the way to go if you've got a brightly colored object and you want to look at it by color. All right, so that's giving us an example of the inRange function. I'm going to take a look now at one last method. And this is one this is kind of complicated. It's the heart of a really cool algorithm that I really like. And it is combining together some ideas from some of the things that came before in a really interesting way, in a way that draws on some statistics as well. So one of the issues with inRange is that we have to come up with those ranges. It's a little tricky to come up with them. It's work. And we often will end up tweaking them to the point where they only work under certain lighting conditions, and lighting changes, and all of a sudden the hues change and it's not working anymore. Back projection is the thing that we're going to look at last. And it's, like I said, a more complicated set of steps, but it does some really interesting things, and it's gives us a little more flexibility. We can actually even track multicolor objects with back projection. So we're going to start, the process here starts by making a reference image. So it could either be a region of interest that you select out of an image, or you could create an image, which is your reference image. And there are two main methods to making a reference image. One is just uses tools from your computer, your regular old tools, not Python, not coding, not anything, to make a reference image. And the other would be to write a program to do it, which is more complicated by far. So if you use the operating system method, you just take a picture of the object that you want. So I'm going to switch over to my code just for a second. I basically took a photo I had and I cropped it down to be this reference image. So this is me holding a bright pink ball in my hand. And so I cropped it, as you can see, so that basically all of the pixels in this are part of the ball. I don't want any pixels of background to be included, because then they'll be included in what we look for. So we need a reference image that is only pixels that belong to the objects we want to search for, because all the pixels in this reference image will go into determining which pixels in a later picture are actually things that we want to look for. So I just actually did this with these tools. I took the picture of me holding the ball. I opened it in the Mac's default image viewer, which is Preview. I think Photos is what it's called on Windows. It can do this as well. And I used its tools to crop just that part that I showed you. And then I saved the original image and put it in next to my Python program so that I could access it. You can also do that in OpenCV. You could determine a region of interest that includes as much as possible of the object and no background, and then you can slice it out of the original image and save it to a file with inRange. That is absolutely fine to do as well, but it might take a little while to do that first step of determining what the region of interest is. When I've had to do that, what I've done is just draw a rectangle on the picture and then move that rectangle around until it's right where I want it to be, and then translate that into a slicing operation that does what I want. All right, I have an example code there was an example program in the reading that was to help you with this process. I'm going to skip that for now, because I want to wrap up this video sometime this year. All right. So in my notes, you can see the picture and the reference image that I gained from it. The next step in the process of doing back projection is to build a histogram of hues from this reference image. So a histogram, you should have remembered a histogram from math class, right? You have some data, you throw it into bins that each represent ranges of values, and then you look at the pattern over those. So you end up with something like a bar chart that shows how many values fit into each bin in the histogram. Histograms are a nice way of simplifying data in computer vision. That's what it's used for in other contexts. That's what we use it for here. So what we do is we have that reference image, that pink image, which is right here, and we convert it to HSV, we look at just the hues. And we take those hues and we make a histogram of them. So we decide how many bins we're going to have, we look at all the hue values, we throw them into bins, and we get a histogram out of it. Each bin in the histogram then represents a section of our hue sequence. So there's a histogram bar for things that are red, for yellow, for green, and depending on how many bars you can have gradations as well. So here I have a little piece of code that I wrote just to show you what that process of building the histogram would look like. We read in the reference picture. I am converting it to HSV. We are then going to call a function called calcHist. We don't have to build the histogram from scratch. There's a function to do it for us. So we pass it the histogram, and we tell it we want it to pay attention to the 0 channel, and none is just fine. Don't worry about that. And this is telling it how many different bars we want, how many bins we want in our histogram, and this is the range of values, minimum and maximum, that will be expected in the data that we're giving it. So if we were looking at a BGR where we were, say, only looking at the blue channel, this would be 0 to 255. But because these are hues, 0 to 180 is what we expect. We are then going to normalize this histogram. Normalizing the histogram in this case makes it scale the heights. So they stay relative to each other, they stay the same relative height, but we're scaling the values so that they add up to 1, the total of them. So we're basically changing each bin into a probability. What's the probability that a certain pixel belongs to our object? Well, what bin does it fall into? All right, and then there's some other technical things here. I've provided a function called showHist, which you can look at in other code sources, and what we get out of that with the pink reference image is this. So most of the pink reference image pixels, their hue values fall into this range. It's almost to magenta, but it's not quite there. And then there are some smaller number that fall into this last range, which are the far end of the magenta end of the spectrum. This histogram is going to be what we use to determine which pixels belong to the object that we want to track. So it's going to try to find anything that matches this kind of pink. The last step is computing the back projection. There's a function called calcBackProject. We pass it, again, the HSV image. We tell it we want it to look at the 0 entry only. We pass it the histogram that we built, tell it the range of values in the histogram, and we just pass it a 1. Sometimes they have these extra inputs. And it produces the back projection. I have a program over here that does this whole thing. And so I think what I'm going to do is switch over to the code and we'll talk through that instead. All right, so I have the function showHist that displays the histogram. Here I am reading in the picture of me holding the ball, and I'm reading in the reference picture. And then it's going to pause for a moment. The next steps are where we're actually doing everything. We're converting both images to HSV, the original image of me holding the ball and the reference image. We're passing the reference image to calculate the histogram, and we do various things to build that histogram, and then we display it so it'll pop up as a window. Then we're passing the original picture in HSV to the calcBackProject, and we're giving it the histogram to work off of. and we'll display the result. So I'm going to run this. Let's go to the desktop view. You can see the result right there on the page, but let's run it. Okay, so here you can see they read in the reference image. This is the other image. They're then going to be, as soon as I hit a space, they're going to be converted to HSV, and then things will proceed from there. And in the end, the back projection looks like this. We get the same histogram as we had before. You can't see it, so I'll put it down here. So it's not as accurate because we haven't as carefully tuned things, perhaps. You can see that it's picking up a little bit of my shirt. I'm actually not surprised by that. This shirt is in that realm of the world, of the hue. So I was actually not surprised that it would pick up part of my shirt and think that it's a similar hue. I could take into account the other values, saturation and value, if I wanted to. Some of these pixels up here, they're just noise because it's basically gray. So some of those pixels ended up with a pinkish hue to them, even though they were gray. I think it's really interesting and kind of spooky that my eyes, which are very, very dark, showed up also. So there are additional things we can do to process this to remove some of the other pieces, but you can see that it works fairly well. And as I said, it's a little more sophisticated, it's a little more robust to changes in brightness, and because of the histogram that it's using. And so there are times when it's actually ideally what you want to do. All right, so again, the main methods, the main functions to remember here are the basic threshold function and the inRange function. The others, they're there if you ever want to explore them, or if you are working on something and you find you need something more sophisticated, then you know that they're out there and you can look them up a little bit more. But this shows you different ways that we can try to use thresholds to help us isolate objects in an image, select things, simplify it, pictures, and that's the primary use for this sort of thing. I'm going to stop there, and I will see you all in the very soon. I will see you all very soon.